Hey everyone! In this video we're going to talk about a confidence interval and a hypothesis test, but it's going to apply to categorical data. So we're going to piggyback off of a lot of our foundational work that we've done in the past couple months, but apply it to a new type of variable and the data that comes from it. Now, we've already talked about confidence intervals, and we've already done hypothesis tests, but that applied to quantitative data. And we looked at, namely, the difference in means. In order for us to have reached the hypothesis testing stage, we first discussed the corresponding sampling distributions. Remember that? And so what we're going to do today in this video is take a very similar path, but we'll be able to condense it in just one video, where we're going to consider a dichotomous categorical variable. Now don't get too caught up there. Dichotomy, so there is just two possible outcomes. That is not unfamiliar to us because we've already discussed proportions. And we will look at a confidence interval for the proportion, and then finally all the steps required for the corresponding hypothesis test. Quick review on notation here. Remember that P with a hat is the sample proportion, which is just binomial in nature, where you take the number of successes and then divide by sample size. And so P hat, because it's from a sample, you can consider it as a point estimate for the population proportion, just plain P. Furthermore, back in chapter, I believe it was 3.6, we saw the first introduction to binomial random variables, and when we discussed sampling distributions of the sample proportion, we also saw that if these two criteria are met, if n times p and n times 1 minus p both exceed 5, then the binomial random variable should approximately follow a normal distribution with the specified mean and standard deviation. And then following that up, that the sampling distribution of the sample proportion would also be approximately distributed normally, again, if these criteria are met, and the center, or the mean, and standard deviation were given by these quantities. So that's a good review there. Furthermore, this is a theoretical construct, right? The whole sampling distribution. But we use the knowledge of how these sample statistics are distributed so that we can estimate the corresponding population parameter via a confidence interval. So here, let's use this info to construct a confidence interval for the population proportion P. Now it looks a little repetitive here, but remember, P, the population proportion, is an unknown parameter, and therefore we're going to replace it with its sample counterpart, P with a hat. And if these two quantities exceed 5, then the sampling distribution should be, again, approximately normal with the mean of P and the same standard error as a moment ago, but we have replaced the P's with P hats. Knowing this information, we can now construct a confidence interval for the population proportion, where we start with the point estimate, that's the sample proportion, and recall we add and subtract the margin of error. In this case, the margin of error is utilizing the standard normal distribution, not the t-distribution. So this is the z value such that 0.025 is in the right tail. And I'm using a 95% confidence here because that is quite typical. And then that z critical value is multiplying the standard error. So I'll go ahead and put that in a nice little box there. And in general, if you wanted to have a confidence interval at any level of confidence with significance level alpha, right, we would just modify the z critical value accordingly. So I think those are the two that are worth putting in a box, but we will mostly use the 95% confidence level per our previous reasons. Let's look at an example to show how we create a confidence interval for a proportion. In a population of nudibranchs, there is a coloration mutation. And in a sample of 580 nudibranchs, that's our sample size, 41 were found to have the mutation. We're going to create a 95% confidence interval for the proportion of nudibranchs with the mutation based on our sample info. Copy pasted a couple stock images here of a couple different nudibranchs. Pretty cool gastropod, really small, really beautiful marine organisms. Now, before we construct this confidence interval first, we need to check that these requirements are met in order for us to utilize the standard normal distribution. So I already identified our sample size n. Our sample proportion is 41 successes, individuals with the mutation, out of our sample size of 580. I just noticed that typo, so I have fixed that here. And now I just need to do some multiplication. So I'll open up R just to perform this simple product. I've got n and p hat defined, and R, please perform those products. As we can see here, both are exceeding 5, so that allows us to state that the sample proportions follow a normal distribution approximately. Okay, so here we go. I'm going to utilize this formula in the orange box up to the left here. Our sample proportion, the point estimate, p hat, 41 over 580. If you want to use a decimal, that is fine, but this is just as effective. The margin of error, we're going to use 1.96 for the critical value, and now we need to multiply that by a pretty big square root here. I need p hat times 1 minus p hat, and that needs to be divided by 580. And if that's not clear, that should all be inside the square root there. I'm going to do some simplification. I'll use R to perform these computations. Let's check it out. So I'm going to type the square root quantity first, which is the standard error. And because I've defined p hat, I can just type p hat times 1 minus p hat and divided by n. So that is all in the square root there. I'm going to multiply that by the critical value of 1.96, and this will be our margin of error. I'll call it MO, margin of error. Let's take a look at the value for MO. About 0.02085. Okay, I'll keep that handy. Now I will create the lower and upper bounds for this confidence interval So I need p hat minus the margin of error, and my upper bound will be p hat plus my margin of error. Let's watch it whip. Okay, no errors, that's always good. And R, can you please display both of these quantities? I'm going to transcribe that onto my display here. Awesome, so our confidence interval I have put into a nice yellow box there. And I think it's worth considering the interpretation of these values, in which, remember, P, the population proportion, is unknown. We don't know what percentage of nudibranchs are going to have this mutation. It's pretty challenging to find out. However, a sample was collected and it was observed that 41 out of 580 in that sample had the mutation. So based on that, what inferences can we make from sample to population? The population proportion is unknown. However, we are 95% confident that that proportion is between about 4.98% and 9.15% of nudibranchs with the mutation. I have a side question here in which I'm asking, can we be confident that the prevalence of the mutation is below 10%? Considering our confidence interval here spans from about just shy of 5% to just over 9%, the answer would be yes. Here's another related question. If we were to perform a hypothesis test for the population proportion to test whether the percentage of nudibranchs with the mutation is less than 10%, would we reject the null hypothesis? We should be able to answer this question even though we haven't formally performed the hypothesis test, because our confidence interval does not include 10%. And remember, the value of the null hypothesis would be that the proportion is 10%. However, our sample data suggests that the population proportion at most is 9.15%, and we are 95% confident about that. So would we reject the null hypothesis? Yes, we would reject the null hypothesis. So even without knowing all the formal steps and formulas for the hypothesis test for a proportion, we can still understand and even predict the conclusion to that test. What we will do now is define all the formal steps to the hypothesis test for a population proportion. So this is sometimes called a hypothesis test for the proportion because it utilizes the standard normal. Sometimes it's called the one proportion z-test. And I'll define the hypothesis and test statistic and p-value, and then we will apply it to this nudibranch example. Okay, so the hypothesis would look like, well, we've got the null and we've got the alternative. Our parameter is p, proportion. Always equality for the null. And in general, we would put, a value hypothesized there. And I like to include in my general definition here that the alternative hypothesis could be a left-tailed, right-tailed, or two-tailed hypothesis. You only choose one, you do not write all three. Because we are using our Nudibranch example, I'll go ahead and in green translate this, because the hypothesis here is that the percentage of nudibranchs with the mutation is less than 10%. So remember that less than is going to show up in the alternative hypothesis. The null hypothesis is always about equality. The test statistic, we would call this Z, S for test statistic from a sample. And in general, we always take our sample value, sample statistic, which would be the sample proportion, and we subtract the hypothesized proportion from the null hypothesis. In the denominator, we always have the standard error. This is the standard error that is presuming that the value in the null hypothesis is true. So this is P naught from the null hypothesis, and P1 minus P over N, and that is all inside the square root. So let's go and plug in our values from this Nudibranch example. Our sample proportion was 41 over 580. Our hypothesized proportion, 10%. And in the denominator is going to be big square root 0.1, 1 minus 0.1 over our sample size of 80. That's all in the square root. I will use R as my calculator here, so you can see how I would type this in. Any calculator would suffice. Okay, so I typed p hat minus 10%. In the denominator, square root of 0.1 times 1 minus 0.1 over our sample size of n, which was already defined, and our test statistic is approximately negative 2.35. Now we use that test statistic to determine the p-value for this test. Because this is a left-tailed test, we know that we want the probability to the left of our test statistic, which follows a z, or standard normal distribution. And I will type that into R in a moment, but graphically what we are doing here, we verify that we can use a normal distribution to estimate the distribution of sample proportions. Our z test statistic is negative 2.35. We are finding the probability that our sample statistic would have been as extreme as it was, or more extreme, assuming the null hypothesis was true. Because this is a left-tailed test, we are finding the probability to the left of our test statistic. There is another way to have done this. I will do this way first in R. We would use the function p-norm. We are finding the probability to the left of our test statistic. And I don't need to type comma 0, comma 1, because those are the default parameters for a normal curve under R's algorithm, but I like to be in control here. We are expecting to reject the null hypothesis. So we are expecting a small probability here. And indeed, we got about 0.009. So I will type that here, that this is approximately 0.0094. And we'll state the conclusion in a moment, but I do want to show another way that we could have approached this p-value. Because we could consider not the standard normal distribution, we could have considered the sampling distribution of p hat, in which the center is p. We already reviewed that. So the center, 0.1. And we are seeing what is the chance that our sample proportion is, which was 41 out of 580. Feel free to use a decimal there, but I know that's down here. We are seeing what the probability of observing that was, or something less than that, under the assumption that the population proportion is 0.1. So we could, again, use p-norm, but use the values from the corresponding sampling distribution. So I will show that here, or we could have typed probability under a normal distribution, our sample statistic p hat. I guess I'll just type p hat since I've already defined it. We want the area to the left, and the center is 0.1. And oh, well, what's the spread? Isn't the standard deviation, I should have given it a name, but I could just copy and paste it from right there. That should be the standard deviation estimate for this distribution. So let's run this and anticipate that the answer, the result of this p-norm, should be the same as our previous, 0.009. Indeed, there it is. So 2 interpretations there to get the probability of observing a result from our sample, like was observed, or something more extreme, under the assumption that the population proportion is 0.1. Okay, so we are ready to state our conclusion. At the alpha 0.05 level of significance, we see that the p-value, 0.009-ish, is less than that significance level. Therefore, we have evidence to reject the null hypothesis that the population proportion of nudibranchs with the mutation, there's evidence to suggest that less than 10% have the mutation. I would like to do another side note on p-value here. This was a left-tail test, but if the alternative hypothesis was right-tailed, then we would have found instead the probability to the right of our test statistic or of our sample proportion. So we would have done p-value is the probability to the right of our test statistic. Furthermore, if the alternative hypothesis was non-directional, remember this is where there's a doubling of sorts, we would need to have doubled this tail area. You gotta be kind of careful the way this is denoted. 2 times the probability that z is greater than the absolute value of your test statistic. So this is, well, if you draw the image, I think it makes great sense, but in order to make sure that your p-value does not exceed 1, you don't want to double a probability that's greater than 0.5, and this prevents that. That will conclude this video. There was a lot of content in here, but we were able to piggyback off of a lot of our previous work. Right, so we've got the confidence interval for the population proportion. We'll mostly use the 95% confidence level. And we were able to anticipate, based on that interval, the conclusion to the corresponding hypothesis test. And so we also discussed how we would structure the null and alternative hypothesis, the corresponding test statistic, and the p-value and R.